We're starting a new chapter today, so I've put a new topic in CavNet. On the left, I've got the part of CavNet open, and this is what the new topic looks like, periodic motion. This next chapter actually has two parts. The first part will be periodic motion, and the second part will be waves. Today, we'll be doing what I call a class lab. That means I'll be doing some labs, so to speak, with the PhET labs. And you'll follow along using this handout, which I'll attach to the assignment and which will be in the topics. It says lab in quotation marks because this is not really a lab you do yourself. It's a lab you watch me do and you answer questions. If you can, I would print this out and write on it by hand, but if not, that's okay. You can follow along. And as I said, we'll be using PhET labs. So we're going to look at how to get there. These are PhET labs. You get to them the usual way, which is Google PhET or PhET Physics. And it gives you this option here, and we're going to be going, instead of electricity and circuits, we're now going to look at motion for the first part of this chapter, and then the second part we'll be using the section on sound and waves. So let's click on motion, and it gives us these, and what we'll be doing today is masses and springs, basics here, and also on the right hand part of the screen we'll be doing the pendulum lab, which I already have open, so I'll open the masses and springs lab. For this one, you might be able to just click on it and it will immediately start. If that doesn't work, download it and then open using the control button. Hold the control button down to override your computer's security and choose open. I know that I can just click on this and open it and get it started. And over here, as I said, you want to have this open and be able to read along or print it out. I will shrink it right now so that I can look at the lab. And here's the pendulum lab on the right. For masses and springs, we're going to choose bounce. We want the objects to bounce up and down. So here I've got a couple of springs, and I can put different bricks on them where the mass is labeled. And on this side, I've got a pendulum, and I can alter the length of the string and the mass and do a few other things. All right, so we'll start by looking at this kind of motion. Get the pendulum moving, and we'll put some bricks on a brick on this spring. All right, let's look at our first question here in the class lab. One object is a pendulum, the other is a brick on a spring. Look at this motion. At first glance, they look very different. This is a brick and a spring, and they're moving up and down. This is a brick on a string, and it's moving side to side. Are they both moving in straight lines? Is the path for each of them straight? And the answer is no, right? The pendulum here traces out a curved path. Whereas this one, the brick on the spring, is moving in a straight line, but up and down. All right, so let's look at that first question. One object is a pendulum, the other is a brick on a spring. Let me tidy things up a bit here. Okay. First glance, their motions seem very different, but what is the same about the motion of these two objects? What seems the same to you? Think about it for a minute. You can pause and then I will answer it. Right? What's the same about them is that the motion's back and forth. It's got this back and forth quality. It repeats. They don't follow exactly the same shape of path. They don't move in the same direction. But what's the same about them is that they go to one end of their motion, stop, turn around, and come back and go the other way. So there's this repeated quality. So that's what's the same about them, this idea of repeating. Now, how is it different from the motion we studied in the first semester? How is it different from a car just going in a straight line at a constant speed? And it's that repeating idea that's different, back and forth, back and forth. Okay, look at question 2. And then I'm going to pull up the pendulum again, and you can think about it. Is the speed the same at all points during the motion? Let me pull this down a little bit so it's a little easier to see. How could you convince someone who disagrees? What demonstration could you do? And for that, and you can learn how to do these PhET labs by watching me, by watching what I do. Okay, our question is the speed the same? And if someone says, yeah, it looks the same to me everywhere, how could you convince them? And when I was in college, a physics professor did this demonstration. he asked us, if you had to be hit by this moving pendulum, if you had to stand somewhere and let it crash into you, where would you stand so that you wouldn't get hurt? And if you think about that for a while, you would stand way over here and you would just let it touch you. Like if you had held your hand out, you would just it would just touch you here and it wouldn't hurt. But if you put your hand here, bash, bash, crash, right? It would really hurt for that thing to hit you there. So it's clear, when you think about it that way, it's clear where it's moving the slowest and where it's moving the fastest. So think about that. Where is this can here moving the fastest? And the answer is right here, smash. Where is it moving the slowest? The answer is here. We can even say it stops for a split second right there. It's moving to the left, stops, moves to the right. Moving to the left, stops, moves to the right. Now look at this one, same idea. If you had to put your hand out and let this thing hit you, you wouldn't want to put your hand here, smash. You put it at the very bottom so it just barely touches your hand and taps it. So clearly it's going slowest right near the bottom and the very top, and it's going fastest in the middle. And you can mark that middle resting place on the lab right here by clicking that, and it makes a little line there. And if you stop it, you'll see what it's marking. It's marking the lowest point of where the spring is when this thing hangs at its length here at rest. Okay? So, is the speed the same at all points during the motion? The answer is no. Right? Is the acceleration constant? So this is a term from the first semester. Think about what acceleration means. It means how the speed is changing. So if the acceleration constant the same? So is the speed always constant? All right, we already said no to that. Well, is it always increasing? Is it always decreasing? So is acceleration constant? All right, let's look at this. Is the speed constant? We already said no. It stops at the bottom, fastest in the middle. Let's mark that middle point. Okay, and stops again at the top. So, well, that could still could have constant acceleration without a constant speed. So let's look at, is the speed always increasing? And think of when the brick comes down to here, it stops for a split second, then it starts to move up. So in this region, as it's moving up, it goes from a speed of 0 to where it's fastest. So going from down here to there, the speed is increasing. But then what happens to the speed as the brick moves this way? And in fact, I think you're allowed to put this in slow motion. There we go. Okay, so, and let's grab this thing and make it move even further. Okay, so where is it going the fastest? Right there. It stops down here, so speed is 0. Speed is increasing. Right there, it's going the fastest. So, as the brick passes through this midpoint and moves up, what's happening to its speed? You can pause and think about it. What's happening at speed from now to now? Fast to stop. Well, here the speed has to be decreasing. So look at the motion here as the brick goes from the bottom to the top. Stopped. Increasing speed, decreasing speed, stopped. So is the speed always increasing at all times? No. Is the speed always decreasing at all times? No. So is the acceleration constant? No. Because if the acceleration were constant, you would just have a constant increase in speed or a constant decrease in speed, but you don't get that. Here we're just looking at basic ideas and words today. If you want to think about what kind of graph you would get if you plotted the speed versus time, that's a good one, and you can look that up on the internet, and you can think about it and try to graph it, and it will match with things that you learn in your geometry class and your Algebra 2 class. But today it's just words, just ideas, yes or no. Okay, so look at this. Is the acceleration constant? Well, we said no, it's not constant because we've got increasing speed and decreasing speed. And it's not always increasing or always decreasing. So the answer to this is no. So now let's think back to the first semester when we had the 4 or 5 equations of motion. They only worked if what? You can pause the video. The equations of motion from the first semester only worked if what? The answer is they only work if the acceleration is constant. And for this motion here, and for the pendulum, the acceleration is not constant. So will our first semester equations of motion work for this type of motion, for this motion here? And the answer is no. See, I have 3 exclamation points. You should write a big no there. They will not work. So we need to learn. That's why we put this in a different chapter in the second semester. We have to learn a new way of studying this motion. And to actually fully get equations of motion for this, you have to have calculus. To just write the equations of motion, you have to have trigonometry and basically be in algebra 2 around that level of using trigonometric functions as functions. We're not going to do that. To prove the equations of motion, you have to have calculus. And no one in the class is in calculus, so we're definitely not going to do that. So we'll take a different approach to this motion. We won't actually come up with equations of motion, but we'll still come up with ways to describe it. Okay, and notice how you can stop this by clicking there, and how you can reset everything by clicking there. All right, turn the page. Now, we're going to, as I said, we're not going to use equations of motion for this, but we're still going to learn how to describe the motion. So let me set up 2 springs here, and let's set up 2 springs with bricks, stop them both, mark their resting position. See how those blue lines mark, okay, where the springs would hang if you stop them. That's where they hang. If you pull them below that, they move up. If you grab it and move it above that, it falls down. But if you put it right at that position, it hangs there because the spring force balances the gravity force. Which way does the gravity force point for this? Down. Which way does the spring force point? Up. And right now they're in perfect balance. Right? They both equal, 1 Newton, right? Because this is 100 grams, so it's 0.1 kilograms. So it would be 1 Newton down, 1 Newton up. Okay, now what you can also do with these is create a line, a movable line. So what I'm going to do is pull this first spring down to here and let go. And for the other spring and brick, I'm going to pull it down to here and let go. Okay, go ahead and read this question. How is their motion different from each other? Now, yes, this one's going faster. It looks like it's going faster and that one's going slower, right? But what if we're going to look at something different here, the idea of how many repetitions it makes, how quickly it's making its repetitions. So what I want you to do is for this one on the left, say to yourself, click, every time it's at its lowest point. So that would be like click, 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 click. Then do the same thing for this one on the right. Click, 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 click. And you'll hear that those kind of sound the same kind of rate. And also you can see that they both reach the bottom of their motion at the same time, and one's not kind of doing that faster than the other or slower than the other and getting out of sync. They're both in sync. So rather than thinking about the motion, maybe this is a bad word, what about the distance they travel? What's different about how far they go? Which one goes farther? And it's clearly spring 2 on the right. That one's going farther. So think about what measurement you can make. What if it's a science, this is a science class, and you need to describe things with a number. What measurement could you make so you could describe this difference between these two with a number? What would you use and what exactly would you measure from where to where? So answer those questions. You, of course, would use a ruler, and you can pull one out right there. What would you measure? Okay, you have 2 choices here with what you would measure. It would make sense to measure from the lowest point the spring goes to the highest point the spring goes, from there to there. I'm doing the one on the left here. Okay? For the one on the right, you measure from down there to up there. Okay? But there's a second way, second distance you could measure instead of that. You could measure from the midpoint, the rest position, where the brick would normally hang stationary, to either the bottom or the top. And that second option is actually what scientists pick and decide is the important distance. There are reasons for that which we won't go into today. So let's do that. Let's do that for the one on the right. And I won't get this perfect. It's harder on a screen than it would be on the board, or one on the left. So let's measure that, and we get about, what's that, 13? About 13 centimeters. And if we did this for the one on the right, okay, we can see that's noticeably different, and we get about 51 centimeters. Okay, so we use a ruler to measure it. We measure a distance. We measure from the midpoint to one end, and I got 13 centimeters and 51 centimeters. All right, we need a name for that. That's clearly something important, something we need to describe with a number, and so we need to be able to talk about it, so we need a name. All right, so here we come to the notes. This is also a handout that's available in topics, and you can either you can print it out or just leave it in topics and look at it online. Okay, so this type of motion we're looking at, this back and forth motion, has a name, and it's the name of this topic, periodic motion. It's motion that repeats identically or close to identical. So that's what we're going to call this type of motion, periodic motion. Here are three examples, the two you're seeing in the lab, and also circular motion is periodic. For instance, the Earth going around the sun. Now, things in real life don't repeat perfectly identically. So identically means close to identical, not exactly the same. Okay? When something makes a round trip, like let's slow this down again, a round trip, starting at the bottom, going to the top, and coming back to the bottom. Okay, we call that a cycle. So cycle is just a fancy scientific word for a round trip. So here's where it starts. Okay, cycle started, we're halfway through the cycle, and now the cycle is ended. That's one complete cycle, one round trip. You can actually you can decide to start a cycle anywhere you want. I could start at the top. So there's the start of the cycle, that's half a cycle, and now that's a complete one cycle. I could also start in the middle, but you have to be careful here because it'll go through the middle. It'll start at the middle, but it'll go through the middle halfway through the cycle. So let's do that. So here's the start of the cycle. That's halfway. And now when it comes up again through it, that's a complete one cycle. Okay? Let's look at this for the pendulum. In one of the options for the pendulum lab, you can do what's called a period trace. And I'll get to that in a second. That will help you see what a cycle is. But let's do one cycle for the pendulum. Okay, so start, end. That's one complete cycle. Away and back, one complete round trip. I could also start in the middle, and that's what period trace does. So I'll put that on now. Okay, it's tracing one complete cycle. They call it period trace, and we'll see why in another class. Okay, so let's try to count along with that and see if this makes sense as a cycle. Okay, start, halfway, done. That's one complete cycle, one complete round trip. Okay, let's do that one more time so you get the idea of a cycle. Okay, moving to the right, to the left, back to the right, to where you started. Okay, all right, and now our final note here, the final note in today's handout notes, amplitude. This is the word I mentioned that we needed. I mentioned we needed it earlier. We need a word to describe this distance from the middle of the motion to one extreme, to either the bottom or the top. So amplitude, you probably heard that word. You probably heard AM radio. That stands for amplitude modulation. That's modulation is a funny word for change, a fancy word for changing something. So this is how radio signals come on the AM band. They modify the amplitude of the radio signal. They change it, and they modify it to give information about how loud the sound is and what pitch it's at. So that's it. The A in AM radio means amplitude. Amplitude is a distance. Okay? And scientists could have decided to define amplitude as being from the bottom of the motion to the top of the motion, but they didn't. They decided it was more useful, it turns out to be more useful to define it from the middle or center of the motion to one end of the motion. There's no universal symbol for amplitude that's always used, but the most common one is a capital A. So that's what I will generally use. Capital A for amplitude. And since it's a distance, the standard unit has to be a what? Has to be meter. Okay, let's keep going in our lab. Now we'll look at two springs again, and this is a reset button, puts everything back to where you started. We're going to put 250 grams on this one and 50 grams on that one. So I have different masses. The springs are identical, but I've got different masses on them. Okay, and I'll pull each one down the same amount. So I'm going to mark the resting position for each of them, and then pull each one down just a little bit. Try to pull them down the same amount, so there's no difference in amplitude. So the thing I'm changing about them, the thing that's different about them is not amplitude. Whenever you do experiments, you try to keep all the variables the same except one. And the thing that I've changed here, the springs are the same, the amplitudes are the same. The only thing that's different about them are the masses. Okay, how would you describe their motion as being different from each other? What's different about it? We say this one's going quicker, we say this one's going slower, that makes sense. So we need a way to describe like quickness. And there are multiple answers. Different people will put different answers here. And different people might come up with different ways to measure this, how these two are different from each other. But I'm going to tell you the standard way we talk about this. And that has to do with time. And so what measuring device do you need to measure time? Well, it's right here, stopwatch. Okay, and what are we going to measure? Think about the words in your notes. Look at the words in your notes. What are we going to measure the time for? What we're going to measure the time for is one complete cycle. So from the bottom of the motion to the top and back down. So look at these two and think, which one takes more time to complete one cycle? For which one is a cycle a longer amount of time? And it's this one, the one on the left. That would take a longer amount of time. And so let's time that. So let's bring our stopwatch over. We're going to time one complete cycle. I think it's easiest if you start when the object is at the bottom. And in fact, in this animation lab and also in a real lab, it's not a bad idea to kind of hold the stopwatch there. And when the brick just barely touches you or comes close to touching you, you start and then you stop when it comes back. So I'll do that. Right? And I get a time of 1.29 seconds, so about 1.3 seconds. So that would be the time for this guy, the 250-gram brick. Okay? So what measuring device would I need? A stopwatch. What would you do? You would measure the time for one complete cycle. And I did that. And let's check. Let's do that one more time and see if we get something similar. Okay, 1.27, 1.29, those are very similar. Now look at this one here. I could do the same thing for this one. All right, let's try that. Okay. 0.58, that's a very short amount of time. It's getting close to the human reaction time. So I don't trust myself measuring just one cycle. And this is not on the handout, but it comes up in a future lab. What would you do? Pause the video and think about it. If measuring one cycle is so quick that you don't trust yourself, it's getting close to human reaction time, what would you do so you could get an accurate measurement of how much time it takes this thing to complete one cycle? You can pause the video and think about it. Well, the standard thing to do is to time more than one cycle and divide by how many you counted. And what's a really easy number to divide by? What would be a really easy number to count? The number 10. So let's do that. Okay. Now notice you start counting after one cycle. You do not do this. Okay, I'm going to do it wrong first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That was wrong because when it first hit the stopwatch, I said 1, but it hasn't even completed a cycle yet. This is like counting someone running laps. You don't start counting when they start. You don't say, okay, 1 lap when they start because they haven't finished yet. So you have to let it finish one cycle before you say 1. So let's do that. In fact, it's not a bad idea to start with 0. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 5.7 seconds. Does that mean that the time for one cycle is 5.7? Of course not. So write down what the time for one cycle would be. And of course you should write down 5.7 divided by the 10 cycles. So the time for one cycle was 0.57 seconds. All right, that completes today's lab. It's a class lab. You don't have to turn anything in. You just have to write done on the discussion board. In the next day or two, I'll write a lab for you where you'll do some things with the springs and the pendulums and answer questions about them.